Hi, I'm Kelly Broadhead, and today we're going to be talking about the Biodesign Lab that's part of the engineering community at the University of Utah. It's part of what we do in biomedical engineering is work on medical device development. And our seniors get to actually have this experience of getting an opportunity to work on a clinical problem. So many of them, or every one of them that comes in will do a capstone design project, and then they will go ahead and use that as an opportunity to really understand what is required to work in the medical device field. And so these projects I'll talk a little bit about later in the presentation come from doctors, respiratory therapists, nurses, physical therapists who see problems that happen in their day-to-day practices, and they share those ideas with us, and then we present them to the students, and the students go ahead and we'll pick ones that they're most interested in and form teams and then work on them for a year. So let's go ahead and talk about some of the things that happen in the design lab or just about biomedical engineering as a whole. So first thing, before I talk about creating something for the body, we need to talk a little about what biomedical engineering does. And so biomedical engineers work on trying to improve healthcare. They focus on taking engineering practice in a range of different disciplines, and they apply those principles to fixing problems that exist within a human body. Now, I call this guy here Fred. Fred happens to have had a few problems in life, and he's had a bunch of different surgeries, including he has a total implanted heart. He has a hip replacement. He is, let me just bring up my little pointer here. He has that hip implant here. He happens to have blown out his knee when he was skiing one day, so he's had to have a knee replacement, and he's broken his tibia on another day when he was skiing. So if you put this all together, Fred really represents a wide range of different technologies that can be used to help people in their conditions. And the products actually require a really wide range of different experiences. And so your exposure to biology would be one of the things that you have to think of in these cases. There's chemistry involved in many of these cases. Mathematics are involved. As an example, you're looking about the heart and the amount of fluid flow and how to model that and get good calculations, or the loading on the knee here and how to do the math behind that. There's medicine obviously involved, and then there's physics. And maybe one of the great cases here of solving all these different things coming together is this case of using a closed loop infusion system for treating diabetes. It has to have a system that can monitor the glucose in the bloodstream. It has to appropriately run a computer algorithm to figure out what response needs to occur, how much insulin needs to be delivered. It has to have a pump mechanism to deliver that amount of insulin into the body, and it has to have a sensor that picks up if it's done the right thing. And so it's a pretty complicated system that really relies on a bunch of different areas to do that. So when we think about, and I just need to get this out of the way here, what biomedical engineers are really engaged in is advancing healthcare. They are trying to make people's lives better. They are trying to bring together a bunch of different technologies and understanding as engineers into helping solve direct problems that happen in day-to-day lives. In this image here, we have somebody that has Parkinson's disease, and this ability to treat Parkinson's disease is really a significant change for many people as they age and they end up with one of these debilitating diseases. Another interesting thing is, instead of just being a biologist, being an engineer actually increases your salary. And so you actually get an opportunity to make more money and solve problems in a more interesting way than just studying biology. So I think these are good things to understand as you think about biomedical engineering as a career choice. So what can you do with a biomedical engineering degree? Well, there's really three major areas that people get a degree in biomedical engineering. We can think of getting involved in research, and that will be something that everybody who does a degree at the University of Utah gets involved in, is doing that research aspect. It can be engaging in the medical device community and trying to improve healthcare. that's many of the students' outcome when they get their degrees done is they end up with a job in the medical device community, working on new technologies or improving things that are already being produced. And there's a range of different roles that can be part of that. And then a number of our students actually plan to go to graduate school or medical school after they get done with their bachelor's degrees. And so this actually serves as a good foundation, giving them the experience that they need to be great doctors, to be great in working in research fields as they go to graduate school, even into business schools. I have a number of students who've gone off and got MBAs after they got their bachelor's degrees or gone off to do law. So it's a growing field. I was just looking at this today. The Bureau of Labor Statistics in the United States says this is a faster than average growing field to get into. So that's one of the important things to be thinking about, is it's still a growing domain, that there is a need for more engineers than what we're producing. The expected strong areas to get involved in is things like computer assisted surgery, so robotics combined with healthcare and being able to do some really sophisticated work in that space. The work in cell and tissue engineering, trying to come up with this composite structure where you got some kind of biomaterial and cells. We're really progressing in the area of using stem cells and getting those combined into something to maybe treat a knee damaged issue and not have to totally replace it the way we're doing it right now. And then we get into rehabilitation, orthopedic engineering, coming up with devices and approaches to help people improve the quality of their life after having some kind of chronic disease occur. Many times you get asked this question: how much can a biomedical engineer make? As a starting bachelor student, after your 4-year degree, you can make in the 60 to 70,000 range. When you get a little bit more education, spend another year in working on your bachelor's degree, you can increase that another $10,000 to $15,000. And the median pay for a biomedical engineer is $91,000. So it's a good field. It's in line with other engineering degrees, and it gives you the ability to work on problems that I think are really important for people to solve today, especially with an aging population and the increasing healthcare costs here in the United States. Like many other fields, I expect that engineers are going to have to be the ones that figure out how to solve some of the problems that exist with the way we do healthcare. So biomedical engineers contribute to the medtech industry. They are involved in helping our local industry grow. And many of us don't realize this, but actually Utah on a per capita basis is one of the highest employment percentages in the country of people who work in the healthcare industry, or in the med tech, I should say, medical device type field. And so some comparable areas would be like the area around Boston or around Seattle that have this kind of density of people that are involved in doing medical devices. Our students, when they graduate, who go into the industry, they end up 70% of them staying locally in Utah. So there's actually jobs that exist here. They're involved in working in these industries to come up with new innovation. They, as an undergraduate, they get exposed to the clinical side. They actually get to go in and see procedures and what's happening in the healthcare side, start to identify problems. And then when they go out and work in industry, they're a source of inspiration to the medical device team that's working on something new. And some go off and decide to become business developers on their own, get that entrepreneurial type background going and get into that space. And so a combination of maybe doing the bachelor's, doing an entrepreneurial certificate in the College of Engineering, and maybe going on and doing a master's gives you that pathway. And I've had a number of students that have actually gone off and formed companies now and are working in that side of the business. So what kind of skills do you need to have? And I divide this into two major areas. One of them is actually, some motivation pieces of it, and the other one's an aptitude. So you would expect that as a biomedical engineer, it's this classic thing. If you go to the University of Utah and you go to your first day of classes, everybody asks you, what do you plan to major in? And they're going to have this response when they hear you say biomedical engineering. They're going to say one of two things, maybe both. They're going to say, you must be really smart. And the second one would be, what is it? I always find that a kind of an interesting paradigm, because if they don't know what it is, and how they know that you're smart doing it? But it is. You have to be smart. You're going to be applying biology and physics. You're going to be putting math, and you're going to have to develop some of these other professional skills like writing and quantitative reasoning and being able to work on teams and things like that. The other one, which I think is extremely important, is the motivation. Why do you want to be involved in biomedical engineering? And for most of us, it's because we're problem solvers. We're really interested in the sciences in medicine, and we want to make a difference in people's lives. And so you bring those three things together, and it really motivates us to get up each day and to really engage in a challenging field. So what can you do as a student in high school right now to get ready? Well, I really suggest you get as much science and math as you can. And one of the things is, as you're going through, try to take AP classes in these areas like biology, chemistry, physics, and math. Take your senior year classes and take the calculus version of AP, not the statistics version, because it'll actually help you with your development in the major. And go along that path as much as possible. And when you get into college, you're going to be ready to start your engineering curriculum. These classes all, if you get scores in them, they will help you either have a stronger foundation in the subject area or actually get you to move ahead of other students that come into the program. So it's to your value to be engaged in these. Your curriculum is broken out into really what I consider three components. The first part is these foundational science areas. Like I said, physics, chemistry, biology, math. You're going to go through and take classes in those in your first 3 semesters. And those serve as a foundation. And even to this point in my career, I still rely on that understanding that I got out of chemistry in your freshman year or out of the freshman physics classes. And you're going to use them throughout your career. So don't think of them as the weeder classes that maybe you have heard people talk about before. When you go to college, you're going to get some classes that are really hard, and they're going to use them to find out if you can do it or not. Instead, think of them as actually things that you're going to carry with you for your whole career as that foundation in engineering. Your last 2 years are really divided into 2 areas. Those are some required classes that everybody has to take in biomedical engineering that cover the different aspects of engineering, like the mechanics side, the electrical side, the computational side. And then instead of engineering electives where you actually get the depth that you need in the major to focus in a particular area. So if you wanted to be really good at designing an infusion pump, then you would take classes in fluid mechanics and coming up with an understanding of that space to go in as part of your major. There are a bunch of different areas in biomedical engineering that you can focus on and get expertise. They're really cool. I've been exposed in cell and tissue engineering areas and biodesign. I've done a little bit of work in mechanics, and that's most of my areas. I've seen colleagues of mine work in areas of cardiovascular engineering, imaging, and neural engineering, and there's even more, but these are the ones that we commonly think of. So now let's take to, flip this a little bit and talk about where we are in this process of creating a medical device. How do we do it? So at the University of Utah, like I alluded to earlier, we get an idea from clinicians. We go out and we talk to them. We get this healthcare need identified by the clinicians. They hand an idea to us, and then we take it into the seniors and have them work on it. And so what do they get? Well, typically they get a problem handed to them. As an example, I'm going to talk a little bit about, you've been tasked with coming up with a better way to measure heart rate and the amount of oxygen in the bloodstream. So we call this an SpO2 device. And you're going to have to use this device because it's really important to monitor this for somebody who's going through surgery or post-operatively. Now, one of the struggles is that if you take a typical way of doing this, you measure it on your fingertip. And when you have trauma or low blood or things like that, low content of blood, your first area that loses circulation is actually your extremities, like your fingers. And so you no longer have an ability to measure accurately what the saturation level is. So how would you solve that problem? What's an approach you could take to get a better reading of saturation levels of oxygen in the blood?
I don't know if this would be possible, but maybe you could put some kind of like device and like put it like close, like on their chest somewhere, like closer to their internal organs to measure it.
That's an excellent answer. I've heard of ideas of maybe putting it up on the ear before, because this area is a little better, putting it on the chest, and then using a reflectance mode of doing it so you get a better reading there. I'm going to show you how my team came up with a solution to this. So let's talk about that. So background, medical devices is a big industry, $155 billion industry in the US. It's interesting, 80% of them are small businesses. So you could actually own the business as an engineer. There are highly innovative, high regulatory burdens. You can imagine having to deal with the FDA as part of this process. It's a really growing area in Utah. There's a lot of people who are involved in coming up with new medical device ideas and turning them into companies. And on a national basis, again, back to this per capita basis, we're like number 2 or 3, sometimes number 1, on the number of patents filed per year in the medtech area in the US. So there are really smart, creative people working in this field in Utah coming up with new ideas, and they're filing patents on those ideas. So what do we do here at the University of Utah to help students get prepared? Well, we have a biodesign our curriculum for the undergrads, and we have Bioinnovate curriculum for the graduate students they can go to. There's also classes on regulatory affairs, how to deal with the FDA and other regulatory bodies in the US, in the European Union. And there's this opportunity to get into doing the business side of getting an entrepreneurship certificate. So I've talked about this in a sense of what is a medical device, and here's some examples like a glucose sensor here, or a catheter used for delivering a drug. And I have no idea what that one is, but I put it on there at some point, so I must have known at some point in my life. This goes way back. We've been dealing with medical devices in this country for almost 100 years in a regulated way. And the FDA first came to be in 1938, said this about medical devices. It's an instrument, apparatus, implement, machine, contrivance, implant, in vitro reagent, or other similar related article, including the component, part, or accessory, which is, and then they give some things. It's recognized as a device. That's one of the steps. It is intended for the use of treating people or animals. And it's intended to affect the structure or function of the body of man or other animals. So it's either intended to use for diagnosis or treatment, or it changes the structure, like I'm making an artificial knee. So these are all considered medical devices. And it isn't just associated with people, but it could actually be for veterinary use. So those are all considered medical devices. So once we decide that it's a medical device and we're going to make a new one, we actually have a process we have to follow, and that's called the design control process. And that's something where we go through, and this is some law that was put around in the 1990s that said, we need to make a safe and effective device. So with these two buzzwords, safe and effective. And we go through and identify user needs, design inputs. These are all these input pieces. And we go through and decide what our design solution is, and we build it. And then we go through and show through testing that what we created is the same as what we wanted to make. So it's this real simple process. When we get done with this part of it, and we go through a bunch of reviews to make sure that we're hitting these milestones, we get to a point that we can actually make the medical device, start making limited runs of it, and then we go in and do testing, what we call validation testing. That is putting it out in the hands of the user, and they will give us a final okay that what we made is what they needed. So there's a whole idea. What you have is an idea, a problem, a need, eventually becomes a solution, and showing that this need solves that. So two parts that we go through that are really critical: this make the good design and then show that the design solves the problem. So why do we do this? Well, this is part of the law. It's systematic. We've got a rigorous process going through. We have, it's team-based, so there are not just one individual, but a team of different knowledgeable people, like maybe somebody from manufacturing and from engineering and quality assurance and marketing, all sitting together and coming up with the design and making the approvals that it's ready to move forward. It's customer focused. We're listening to the users telling us what they need in the project. And it's robust, meaning it actually has abilities to stop a project that's considered to either be ineffective or not safe. And so we want to make things that aren't going to cause harm to other people in this process. And obviously it's required by law. The FDA has this mandate that if we don't do this, they can come and shut us down as a company, and we can't get our product actually approved to sell it in the US. So this is the input stage. This is one of the projects. This is the SpO2 sensor that I was talking about. They came up with this need statements of what this thing needed to do. And the device must display arterial oxygen saturation and heart rate readings at intervals no longer than 8 seconds. And it has to be able to tell when there's a warning condition, and it must fit inside the esophagus. So here's their solution. They want to put it down in the esophagus. It makes sense if you think about this thing. If you don't have good flow here, I bet there's really good flow in this compartment. And so they're going to go through the solution. And they came up with the concept of what the thing would needed to be, and then they started laying out their engineering design for it. And there'd be electronic design and mechanical design. And this is an example here of their mechanical design. It's an engineering drawing showing the different pieces of it. And they would lay all this out, and this would finish off the design input piece. And then the next phase that they would go into is design output. And so they would go into the lab, the biodesign lab, and they start building these things. And we have tools like 3D printers and 3D milling machines. And they go through and do all this build phase of making something. And that's what my students are doing right now. And then they would go in and finish it by doing their verification testing and getting the measurements for it and showing that what they made is actually what they intended to make. So you can see that first loop where they're actually showing the outcomes, meaning the inputs. So here's some, I'm just going to go through and just talk a little about the lab, what we have in there. We have a bunch of 3D printers that are available. So from different companies, they do different things. Some of them are filament printers. This one is a resin printer that uses light to make it cure. So we have the ability to make things. We have machining equipment. And the machining equipment includes the ability to do 3D machining approaches, like our big 3D or milling machine here, or router tables to build things out of wood. We have laser cutters in the lab, and we have a smaller milling machine for doing printed circuit boards. Then we go into the testing equipment. We have mechanical test stations for making sure that the device is strong enough. We have inspection equipment for measuring the size of things, so we can actually measure things on that device. We have electrical instrumentation to probe the electronics on the device, things like oscilloscopes and function generators. So we have all this kind of capability in the lab. Now, not only do we have these capabilities in the lab itself, but the University of Utah has a bunch of different maker spaces that exist that students have access to. A couple of them that we use all the time for our students is the Center for Medical Innovation. It's in the health sciences community. We're close partners with them. They teach our clinical immersion classes, things like that. And so they have a lab that's very much similar setup as what ours is, a lot of the same equipment. And then the Lassonde Makerspace has a maker lab. They have 3D printers. They have a fabrication shop that you can make things in. And these are all tools that are open to students at the University of Utah to use. So you don't have to be, as an example, living at the Lassonde studios to use that space. It's open to all students. So here's a project that we worked on. This one is actually a biodesign project that we started about 12 years ago. And a student team worked on it for that year. And it's actually grown from that point to being into doing clinical studies now. And the design is actually to go into a hard boot and allow somebody to go about their activities when they break in maybe their tibia and see how much loading they're putting on the bottom of their foot. Now, if anybody's ever done that, you're told to start with, you're not supposed to put any weight on your boot for the first like 4 weeks. So you're supposed to be totally on crutches. So this can monitor that and record what's going on. And then you're told that you're supposed to start going into like toe drag mode, where you can touch the toe down but not put much pressure. And you do that for another 4 weeks. And then you go into another mode where you can actually get off the crutches and start walking on it. So you go through these steps, and then after that, you get out of the boot. Now, the interesting thing is our Dr. Kubiak, who's come up with this idea that he does all these surgeries and work in this space. He says, we've had this paradigm of how we treat people, but we don't know why. No one's ever done any controlled study on it, but we just do it because we think it's the best way to do it. And so he came to us, and the undergraduate said, come up with a design that actually allows us to measure the pressure that's happening, and we can correlate that then with healing. And so they're doing that and coming up with these different approaches. So it has the ability, this is what it looks like on the inside, the sensor and this gel structure that goes around it, and they can measure the pressure that's happening in the foot and the type of pressures that come off of it. And so this has gone, into boots that they're using, and now we're working on a new generation that actually would go into the insole of your running shoe. And so once you're out of the boot and don't need that anymore, then you'd wear one that's in your shoe, and you can continue to monitor for the next 3 months to see how they progress. So we're essentially out of time. I was going to show you a little video here, but we're not going to do it today, that talks about some of the involvement that you have as an undergraduate, and you can do these things. And I'll just start this as we finish, and you can hang out for a little bit before you start your next session. But these projects are really cool. As an undergraduate, you get to work in a design project for a year. The other thing that as a biomedical engineering student is you get to go through and work on a research project. So is there any questions? I know we went through a lot pretty fast. It's like going to a lecture. So if you don't have any questions right now, remember that you can go to an advising session after the 3 presentations, that you can talk to one of the advisors or one of the other faculty members. I'll also be there, and we'll be doing breakout rooms. And so you can ask some questions there. You want to see the slide on salaries? The all important part, right?
Excuse me, I'm sorry if I missed it, but what was the solution that you and your team got for measuring? I don't remember, something about.
Yeah, saturated oxygen.
Yes, yeah.
Okay. The team's idea is to come up with a device that would be on the end of a catheter that would go through the mouth and down into the esophagus. And the reason that they want to put it in the esophagus compared to the other option, which would be to put it in the trachea, is the trachea already has this intubation tube setting in it, and the esophagus doesn't have anything going on. And so it's collapsed. It makes a nice environment where the sensor would be sitting down in there, and then the esophagus would collapse around it and give good contact with the sensor and be able to give the readings that you need.
Okay, I understand now. Thank you.
Yeah. So what's it like to do school in the modern days for a student at the University of Utah with COVID? This is the way a lecture is often done, is we would do it through Zoom and have a discussion section and talk about things. Of course, we're expecting that by the time you get to the U, it'll all be solved and be back to normal.
Yeah, my classes are just like this, except there's no discussion at the end because, everybody's shy and quiet.
That's a given. Same thing happens in my classes with seniors in college. They're still shy and quiet. I have to ask them hard questions, and then I have to use a random generator that picks a person that has to answer the question. So some days you get the unlucky draw.
I am wondering, since you guys, I'm sorry, you want to go first, Taylor?
Yeah, sure, thanks. So I was just wondering, Kelly, what do you teach?
So I teach this class here that I'm talking about, biodesign. So I work with students for a year on working on medical devices. And then I also teach a class on how to write your research projects. And that includes dealing with honors theses. So if you ended up doing an honors degree, then you would work on your honors thesis with me. So.
Okay, yeah, because I was in Erica's class, her 1010 class, and she kind of, yeah, they talked about it. And I'm pretty sure all the seniors, when they came and visited, said that biodesign was like the hardest one. That one was like biomaterials. That or biomaterials. I don't think it's
or biosystems. It's like a toss-up.
Biosystems might be it.
If you put them all together, then you know it's the hardest because it's just hard. So there's a little bit of scheduling that when we lay out a schedule as an advisor, and I do advising for the program along with Erica Fernley and then Heather Palmer. And when we do advising, we try to figure out workloads for students. How many hours are they working outside of school? What direction they want to go with a career, and figuring out a curriculum. And sometimes the curriculum is done in 4 years. I've seen cases of students being done in 3.5. And on the other extreme, you get students who take 6 or 7 because they're doing full-time jobs. And so we can tailor this to where you are in your life and what you need to have as far as a mixture of job and engagement in school and maybe internships with companies, things like that. You know, that's one of the big things I think is a lot of the students who want to go and work in the medical device field is they do internships doing the same thing that we're teaching in this class, but they do it in a real job as well. And so it really reinforces, because they get to see it as a class project working on a medical device for us, but then they go out and they work for a company like Edwards Life Sciences where they're working on something to treat people's heart disease. And so it gives them this opportunity to work in both environments, and it really gives them an opportunity to get a better job and they get done. And the nice thing is you get paid. Right now, most of our interns are getting between $15 and $20 an hour. So typically you can start doing that after you finished your sophomore year. Okay, I will have to let you go. We're going to have another group coming in here in a moment, and so you guys can move to that next presentation. Thanks for coming today.
Thank you so much.
Thank you.
Yeah, thank you.
Thanks.